So, let us write that down. We now intend to build what is called the Daubechies family. You know, this name is actually the name of a mathematician, scientist, whatever you might want to call her, and the full name is this. I believe this is correctly pronounced as Daubechies, but I could be wrong. I think we could just probably say Daubechies and be content. So, anyway, we now intend to build the Daubechies filter banks, or Daubechies MRAs. And the feature of these Daubechies MRAs is that as we go to senior members of the family, as we go to increasing seniority, there are more and more 1 minus Z inverse terms. So, on the high pass branch, we are effectively cancelling or killing higher and higher order polynomials. So, the other way of looking at it is, if you are cancelling or killing them on the high pass branch, they must go to the low pass branch. So, we are retaining more smoothness on the low pass branch. That is another way of looking at it. And in addition to doing this, we also want the same kind of analysis and synthesis filters. So, all this together leads us to a special class of filter banks, which we shall now put down explicitly. And these filter banks are called conjugate quadrature filter banks. So, we are looking at one class of what are called conjugate quadrature filter banks. Now, the describing equations of these conjugate quadrature filter banks are very simple. We start from the Elias cancellation condition. The Elias cancellation condition says G 0 z needs to be essentially H 1 of minus z. And we have the freedom to put plus or minus here. Similarly, G 1 z needs to be correspondingly minus or plus H 0 minus z. Now, taking inspiration from the Haar, let us take the following choice. G 1 z is minus H 0 minus z, and therefore, G 0 z is then plus H 1 of minus z. Now, you know, we will keep away the factor of 2 for the moment, because after all that factor can be absorbed in the C 0 that we have allowed. So, with this substitution, what do we get? The tau 0 z, then of course, tau 1 z is identically 0 by construction. But tau 0 z takes the following form then. Tau 0 z takes the form half G 0 z, which is essentially H 1 minus z times H 0 z plus minus H 0 minus z times H 1 Z. So, we have an interesting situation here. We have this H 0 Z H 1 minus Z product. H 1 Z is essentially a high pass filter. H 1 minus Z therefore, essentially becomes or aspires to become a low pass filter with a cutoff of pi by 2. So, here you essentially have a cascade of two low pass filters with cutoff pi by 2, and correspondingly this becomes a cascade of high pass filters with cutoff pi by 2. And you are effectively saying that the overall system function with this cascade of low pass filters of cutoff pi by 2 and this pair of high pass filters with cutoff pi by 2 must go towards a perfect reconstruction situation. That is the interpretation of this equation here. So, we now focus on H 1 Z. You see, if we look at the Haar, once again, there is a relation between H 0 and H 1. In fact, what we are trying to say is, we of course need to relate the synthesis to the analysis for the purpose of alias cancellation. But now we have a perfect reconstruction requirement. So, we want this tau 0 z to essentially go to a delay and a multiplying constant. Now, that means you need a relation between H 1 and H 0, and one simple thing to do is to make H 0 z related to H 1 minus z. That is what we have actually done in the Haar. If you look at it carefully, in the Haar case, H 1 minus z is essentially 1 plus z inverse by 2. So, H 1 minus z and H 0 z are very closely related. Now, let us generalize this. In fact, the only catch is, we will later on need to make a little adjustment here. So, at this moment, even if we simply accept H 1 minus z to be equal to, you see, in the Haar case, this is equal to H 0 z. But we may need to make a little adjustment here. So, what we will do is, we shall in general note that H 1 or rather H 0 should be related to H 1 minus z. So, in the Haar case they are equal, but in general we will ask for a relation, a very close relationship. The other way of saying it is that if you replace z by minus z in H 0, you should get the H 1. So, what we are saying is choose H 1 to be derived from or to be slightly modified from H 0 of minus z. Modified in what way? So, in fact, here again there is a little bit of an issue. What I am now going to do is to put down a choice for H 1 by knowledge or by an exposure to the filter banks that I have and justify it later. So, you will have to bear with me for a little while, not too long, maybe just about a lecture. I shall put down the choice here, I shall partially justify the choice in this lecture and completely justify the choice in the next lecture, where we once again look at the whole system in toto. So, let us choose H 1 z not to be H 0 of minus z, but H 0 of minus z inverse. And we will also allow for the possibility of a z raised to the power d here. So, we will say minus d. We will allow for this possibility. If we do that, in fact, we can verify for the case of Haar. It is very easy. For the Haar case, let us take z inverse times h 0 of minus z inverse. And indeed, h 0 of minus z inverse for the Haar case is essentially 1 minus z by 2. And then if I take z inverse times h 0. So, if I multiply this by z inverse, multiply both sides by z inverse, I have essentially z inverse minus 1 by 2. So, we are doing well. Now, let us make this the most general case. So, we will consider h 1 z to be of this form, z to the power minus d h 0 minus z inverse, and write down the tau 0 z for this. Tau 0 z would become half then h 0 z h 1 of minus z. So, h 1 of minus z becomes minus 1 raised to the power minus d times h 0 z inverse. Now, minus, you see you have g 0. So, again now you have g 0, and let me put back the expression for you just for convenience. We want tau 0 z to be this h 1 minus z times h 0 z, for which we have this term h 0 z into h 1 minus z, all right. So, you have z raised to d there, and minus h 0 minus z times h 1 z, and h 1 z we have accepted to be z raised to the power minus d times h 0 minus z inverse. So, we have z raised to the power minus d here. Now, what we intend to do in the next lecture is essentially to look at this expression. So, we have h 0 z, h 0 z inverse here, h 0 minus z, h 0 minus z inverse there, the z raised to the power minus d terms there, and of course, you have a minus 1 raised to the power minus d here and a minus 1 here. We need to choose d strategically, it is clear. And then we also need to put some conditions on h 0, so this indeed becomes a perfect reconstruction situation. We shall complete this in the next lecture and take it further from there. Thank you.